Hello, class, and welcome to lesson 3 of laboratory activity section 2. Today, we're going to be dealing with heating and cooling curves. And so our major understanding for today is that there are 3 phases of matter: solids, liquids, and gases, and that they have different properties. Also, heat is a transfer of energy, usually thermal energy, from a body of high temperature to a body of low temperature. And thermal energy is associated with the random motion of atoms and molecules. Okay, so previously we discussed heat transfer between 2 different objects of different temperatures. Today we're going to talk about how the addition of heat energy to a substance changes its temperature as a function of time. Okay, and so for heating curves, if heat energy is added at a constant rate over time, then a heating curve can be created by observing the substance's change in temperature. Okay, and so specifically, we're going to look at a heating curve for chlorine, and our New York State chemistry reference table will be very helpful here. If we go to table S and we go to atomic number 17, which is the element chlorine, we'll find the melting point and the boiling point for chlorine at standard pressure in degrees Kelvin. Okay, and so for a heating curve, imagine we took a sample of chlorine and we heated it at a constant rate starting at 0 Kelvin. And what we'd notice is initially at 0 Kelvin, our chlorine would be in the solid phase. Okay. And for phases of matter, we have 3 different ones, right, that we're going to discuss for this course. Okay. One of them is solid. And a solid is a rigid structure with definite shape and definite volume. Okay, and so if we're going to represent that with what we call a particle diagram, we can draw the particles as tiny circles, and we can just draw them in a way that represents that they are rigidly in place and that we have a structure that's independent from the container. And so do something like that. Okay. Now, this substance is in the solid phase up until it gets to 172 Kelvin. And that's where it undergoes a phase change. So this is our melting point. This is our melting point for chlorine. Okay. And but let's say let's identify our initial point as point A, and the point at which it reaches 172 Kelvin as point B. Okay. But we can say that between point A and B, so between A and B, we can say specific things about the change in energy that's occurring for the substance. Okay, so because temperature is increasing here, we can say that our kinetic energy is increasing. And going forward, I'm going to just write Ke for kinetic energy. So kinetic energy is increasing. Okay, and it's important to remember, we'll write it right down here, that temperature is a measure of average kinetic energy for particles in a sample. In a sample. And this is an important concept because basically what it's telling us is that if temperature is changing, our kinetic energy is changing. And if temperature is not changing, then our kinetic energy is staying the same. Okay, but here our temperature is increasing. It's going from 0 to 172, so our kinetic energy is increasing. However, our phase is staying the same. So since our phase is staying the same and our solid only has so much potential for absorbing thermal energy, we could say that our PE, or potential energy, here I should write it out the first time. So potential energy, which we'll call PE, that stays the same. So going forward, I'm going to write PE for potential energy. Okay. So now, once we reach our melting point, our substance now is going to undergo a phase change. And so we will have both solid and liquid okay? And our temperature will not change as long as we're undergoing this phase change. So our temperature is going to remain 172 Kelvin as long as we're transitioning from solid to liquid. Okay, and so to draw a particle diagram here, I'm going to continue drawing part of our substance in the solid phase, having a rigid structure, and then part of our substance in the liquid phase. And it's important to note that a liquid, right, has definite volume. So there's no space between the particles, definite volume, but no definite shape. Okay, and so I'll draw two liquid particles down here on the bottom that have fallen off our rigid structure. Okay, and then we could say that this is point C, and we can say that between, I'm trying to write this over here, between B and C. So during our melting point, or we have a phase change from solid to liquid, and we'll represent liquid by cursive L. Because we're undergoing a phase change, our PE is increasing. Okay, there's greater potential for absorbing thermal energy in a liquid than there is for solids, so our PE is increasing. And because our temperature is staying the same, and temperature is a measure of the average kinetic energy of particles in a sample, we could say our Ke stays the same. Okay. So once our entire substance has undergone this phase change, now we will be completely in the liquid phase. Okay. And so again, I'll draw our particles in the liquid phase, taking the shape of the container, but again, having definite volume. And we can say that if this is point D, we can now say between C and D, we have Ke increasing And again, that's because temperature is increasing. And since our phase is not changing, we could say our PE stays the same. Okay. And so at this point, our liquid is going to continue to increase in temperature until it reaches this point right here, which is our boiling point. And at this point, our substance is gaining enough thermal energy where some of the particles can now escape into the gaseous state. So we will have both the liquid and gas states here. Okay, so I'll draw some liquid particles on the bottom. And then for gas, we have no definite shape. And no definite volume. So there's a lot of space between our gas particles. So we can draw them, oops, wrong spot. So we can draw them here. Okay. Okay, and so basically anything or any chlorine sample that's below 239 but above 172 will be in the liquid phase. And any chlorine sample that's below the melting point of 172 will be in the solid phase. Okay, but at these points, they'll be in phase transition. You'll have both the solid and liquid phase at 172 and both the liquid and gas phase at 239. Okay, so now let's say this is point E, and we'll say between D and E, okay, we have a phase change of gas to liquid, or I'm sorry, liquid to gas, okay? And we have our PE increasing as a result of this phase change. And our KE is staying the same. Okay. Now, once our entire sample has transitioned into the gaseous state, then we will have only gas particles, right, in our sample. Okay. And so we could just say after point E. So after E, we have an increase in KE. So KE increases. And our PE, again, stays the same. All right. So without all these particle diagrams and notes drawn on this, a heating curve looks a lot like this right here, where we have our substance heated over time. We have these sections where temperature is not changing. Those are our melting and boiling points. Okay. And if we wanted to represent this as a cooling curve, it would look exactly the same, just flipped over, where if we start off as a gas and we allow it to cool over time, we'll find that the kinetic energy is decreasing until we get to a phase change. Then our potential energy is decreasing as our substance is condensing. Okay, and then once our entire substance is condensed into the liquid state, then we'd have our KE decreasing here, all the way until the point where our substance starts to solidify or freeze, and then that would be our freezing point or fusion point. And then once our entire substance is freezed, due to a decrease in potential energy, then the temperature will decrease again and our kinetic energy will decrease. Okay, so that is a summary of heating curves and cooling curves, and we'll quantify the amount of heat being transferred next time when we talk about specific heat capacity, heat of fusion, and heat of vaporization. Thank you. See you next time.